Record. Happy Monday. Today we need to talk about the final topic that's fair game for the upcoming midterm exam. So that's the main stuff for today, is talking about this fundamental theorem of line integrals at 16.3. I guess before we get into the math, just a reminder that, well, you have a midterm coming up on Thursday. So please make sure that you have a plan to study for it from now until Thursday. Wednesday's class will be a review class, similar to what we had before our first online test. And so I have a document in D2L already posted and whatnot that has some problems I think that'd be good to kind of review. And we'll have you vote and all that sort of stuff, just like last time, to determine kind of which of the topics you want to for me to discuss in person versus which ones can I just post the solutions online. I think administratively, that's really everything that I wanted to make sure that I told you. Any questions about anything before we jump into the math for today? Where do you take your midterm? Recitation, good. How long is it? 45 minutes. How many questions are on it? 8 to 10 or so seems about right. We've had 30-minute quizzes that have 6 questions on it. Our first online test, which was 60 minutes, had 12 questions on it. So we seem to be averaging around 5 minutes per question. So at 45 minutes, you should expect around 9. Of course, if it has 8 or 10 or something like that, that's also probably fine. But somewhere around 9 is a good guess. All right, cool. So then, math time it is. So in the pre-class video with the fundamental theorem of line integrals, we talked about how, in some cases at least, it seemed like the line integral didn't depend on the path that we took. And so in this first example here, we parameterized, in several different ways and traveled along these curves and found out that no matter what we did, we always got the answer of 2. Again, when I'm thinking about line integrals with vector fields, I'm thinking about the amount of work that it requires to push a particle or something like this, the vector field's going from 0, 0 to 1, 1. And so it's kind of rather remarkable that no matter how you travel, this vector field is always doing the same amount of work. That's not obvious that that would happen. And yet it seems to. And so then we go into basically some technical math stuff. I guess I'm jumping ahead a little bit here. This first problem, it lend itself to understanding an idea called path independence, that sometimes it does not matter the path that you take, it only matters the starting and the ending point, right? And so in this case, we talked about path independent line integrals and got a definition there. And it turns out these have something to do with conservative vector fields. So this is going to tie in very well with what we did in 16.1 with conservative vector fields. This is the bit here that kind of gets into the weeds. We're about to do a theorem called the fundamental theorem of line integrals, hence the name of this section. And just like any math theorem, it has hypotheses that need to be true. It's not going to work in every single scenario out there imaginable, but under nice scenarios and nice situations, the fundamental theorem of line integrals will be true. And so in these hypotheses, you need to know something about regions and all this sort of stuff. And so here was a time to kind of dump a bunch of it feels like math jargon, but these are important definitions that will help determine when the fundamental theorem of line integrals is true and when it's not. So that was all of this bit here, is just kind of, a bit in the weeds. But again, this would be important for the hypotheses for the fundamental theorem of line integrals. So that's what this was all about. And then the very last bit is that we did find a potential function for this line integral. And this is where we need to kind of transition into the new stuff for today. So I get a little bit more to this story here, but before we jump into the new stuff, were there any questions? Anything that maybe I could spend another minute or two explaining about anything from the pre-class video? So here and then here.
For D, for like the previous page, why do we just say 2 again? Like, which model or what?
Oh, yes. So the question is, for this part here for D, why did we just say 2? And I hypothesized that it would be 2, right? Based on the work from the easier ones that we could actually calculate, we kept on getting the answer 2. And so, yeah, D is really more of a hypothesis, more of a guess than, I didn't actually do the calculation. This would be kind of crazy to do all that parameterizations and whatnot. So we think it's going to be 2, but we would need to prove this. And the way that we're going to prove this is with the fundamental theorem of line integrals. So that's kind of leading into what we're going to be talking about here today. And then here.
Said that in order for it to be conservative, you need to take the gradient of it come from another function.
Yes.
But you only showed it the scalar because, like, for force, the gradient of p equals the force, or gradient momentum. So can it come from another vector?
So the question, as I understand it, and I feel like I'm missing a piece here, is that for conservative vector fields, they need to come from the gradient of a scalar function. And the question was, does it have to be a scalar function, or can you take the gradient of maybe a vector field or something like this? So with our definition, gradients only make sense with scalar functions. So later on, we'll talk about something called divergence and curl, but that's not until 16.5, in which case you do take partial derivatives systematically of components of vector fields. And there'll be an array of theorems that kind of go along with that. But for the time being, we're just doing gradients of scalar functions, and life is grand. And so bask in the simplicity of just doing gradients of scalar functions rather than applying, well, this would be called the del operator on other vector fields. So it's coming, it's not today. Good. Any other questions? Okay. Well then, again, the last bit here is that we found a potential function for this vector field, which seems to be path independent, that it doesn't matter which path you take, it just matters your starting and your ending point. And so what I'd like to start today's new stuff with, jumping over here, is showcasing that, again, with our function, and I'm just going to write it here so I don't have to remember or jump back and forth a bunch or anything like this. So if this is our function for our potential function, right? Then if we go ahead and we calculate out and we plug in our ending point and we subtract away the function's value at our starting point, well, then I'm going to get 1 squared plus 1 squared is 2. 0 squared plus 0 squared is 0. And so I get 2. And this was that same answer that we got in A, B, and C. And I hypothesized that it would be also the answer for D. This is important because, I mean, this is essentially f of B minus f of A. This is the good old stuff from Calculus 1, the fundamental theorem of calculus, right? We've showed that some integral is equal to f of B minus f of A, right? And so hence the name, the fundamental theorem of line integrals. It's very akin to the fundamental theorem of calculus back from Calculus 1. And so let me go ahead and write this down here, but we'll put it in a box here shortly as well. So this integral that we were calculating out turns out to be f of some ending point minus f of some starting point, f of B minus f of A. Again, these are now points in a plane rather than just values themselves, right? From the fundamental theorem of calculus, it was f of B minus f of A, and B and A were values. But these now have, these are points. A and B are points, and they have x and y coordinates. So we plug those things in. So let me just remind you here. Reminder. So this is very similar to when we were integrating back in Calculus 1. The fundamental theorem of calculus said that when you integrate this, a derivative function, or you find the antiderivative, and then you plug in B, you plug in A, and you subtract. All right, so let's now put this result in a box. And here's where you see some of these definitions and whatnot coming in that we need. So C needs to be a smooth curve joining point A to B in a plane or space. So we'll be doing this in 2 and 3 dimensions. It needs to be parametrized. So we have R of t here. Let f be a differentiable function with continuous gradient vector. So again, this is some of the niceties, some nice function here, on a domain D containing our curve. Then in that case, if all these hypotheses are met, then just as we said, this line integral, which is calculating out the work, does not depend on the path. Instead, you just need to find the potential function and then do an f of B minus f of A sort of situation. again, this is relying on us being able to find a potential function. So this vector field here needs to be the gradient of some scalar function. In fact, another way to write this, right, is the gradient of f dot dr, line integral over this, f of b minus f of a. And I just want to point out here kind of the similarity between these statements especially, right? Back in calculus 1, when we took a derivative, right, it was just f prime, there we go. But now here in calculus 3, right, if you wanted to take derivatives, right, well, there's different variables that you could be taking the derivative with respect to. You can do with respect to x, or with respect to y, or with respect to z if you're in space, right? And all of that information, your x, your y, and your z derivative, if you have one, are all embedded in this vector right here. So this is essentially a derivative vector. It houses all of your derivative information. And so essentially this is the derivative here. And it's very, again, akin to what we did in calculus 1. All right. Any questions on this before we continue? All right. Well, I have a quick corollary to this. So once you have the fundamental theorem of line integrals, if you imagine you have a closed curve, so we have already brought up closed curves before back in 13.1 when we were parametrizing things, right? And when we had closed curves, curves that started and ended at the same spot, right? Or went in a loop or something like this, we typically parameterize these with sines and cosines rather than with x equals t or y equals t or z equals t. So these have come up before. But if you have a nice closed curve, that means you're going to have a starting point equaling to the ending point. Then what do we know? If this satisfies the conditions for the fundamental theorem of line integrals, what do we know about then this integral here? It should be f of b minus f of a, right? Right? Good. And so I don't know what f of b or f of a are, but I know that they're the same. So maybe they're both 5, or maybe they're both 7, or maybe they're both negative 13. But the big thing here is that, well, it's going to be f of b minus f of a. So 5 minus 5, or 7 minus 7, or negative 13 minus negative 13, right? No matter what, you're going to end up with getting 0 here. All of a sudden, I got really paranoid that I never hit the record button, so I had to check. All right. So yes, with the fundamental theorem of line integrals, if you have path independence, then if you have a closed curve, f of b minus f of a is just going to be 0, right? Because whatever the value is at your starting or ending point, and again, you could choose a different starting and ending point, right? Maybe we parameterize it in a different way, and we start and end over there, right? Still, because it's the same value, right? Whether it's whatever, 14, 100, right? F of b minus f of a, 100 minus 100 is still 0. So yes, question. So yeah, I mean, the particle absolutely has to do some work to get there, right? However, if we're talking about how much work is done by the vector field, essentially what I imagine when I'm thinking about these things is that we're on a roller coaster, right? And again, the wind is not, in this case, the wind I'm thinking about is the vector field, right? The wind is not strong enough to knock the car off of the roller coaster. We're not talking about some tragedy or anything like this, right? It's staying on the roller coaster, right? And you're going to go from point A to point B no matter what, right? There's enough other forces and whatever mechanics in the system to make sure that you get from point A to point B. But the question is, how much does that wind affect, right? Does it help in general, right? Is the wind at your back? Does it hurt, right? Does it like, and of course, these days, roller coasters are sophisticated and can slow you down if you're going too fast and speed you up, you know, kind of, and be a little reactive like this. And so it's the same thing here, is what I'm imagining, is that, again, you're going from point A to point B no matter what. How is the wind influencing? You know, is it helping overall? Is it hurting, right? It's not the only factor that's going to take you all the way around, you know, your roller coaster ride, but it can help or hurt. Yes.
The pre-class videos, like we had that like thing and we said it's like path independent there, and it was like we did the same thing like f dot dr.
Yes.
Like for each case, but like now we're saying it's like 0 and everything. So.
If it's a closed curve, yes. But before we were going from 0, 0 to 1, 1. So this is not a closed curve. So if you have a closed curve, yes, it'll end up being 0. If you don't have a closed curve, this will still apply, and you can do your f of b minus f of a. All right, so let's see. As of right now, we like conservative vector fields because they're path independent. And we like them even more because if we can find a potential function, then we can evaluate line integrals quite quickly. So my questions become, given a vector field, how do I know if it's conservative or not? So, of course, we've had some pretty nice ones, and maybe you can just look at them and convince yourself that it should be conservative. But in general, if you have a nastier one, for instance, we're going to be doing this problem down here, so you can already peek at this vector field. Can you just stare at this and tell me if it's conservative or not? It seems kind of difficult. So we're going to learn a way of how to identify when a vector field is conservative and when it's not. And then second of all, suppose that we have a conservative vector field. The next question that we have to ask ourselves is, how in general do you find potential functions? Because again, we dealt with a very easy case where you could almost just look at it and kind of do a bit of a guess and check for a potential function. But it turns out that this will be a conservative vector field. Can anyone just look at this and tell me what the potential function is very quick? Right? This requires a little bit of work, I think. So that's what we're going to be building up towards here in the next part of the lesson. So the first bit here is, how do we know if we have a conservative vector field? So I'm going to suppose that we have a vector field in a plane. So we just have p's and q's for the time being. And we have a nice scenario, right? So we have an open, simply connected region D. P and Q have continuous first order partial derivatives. So again, it's kind of a nice setup here, which again, many of the problems in our class fall into this category. Otherwise, we just can't solve them. And the conclusion goes, if you have Q sub x equaling P sub y, so that's, if you want the partial notation, we can do that too. Q partial derivative with respect to x, P partial derivative with respect to y. Then my claim is that F is a conservative vector field. I want you to notice that, so if it is a conservative vector field, just kind of on the side here, then again, this means that our F is actually the gradient of some scalar function, which means that P is going to be F sub x and Q is going to be F sub y. Essentially, what this is saying here is that if we then take these partial derivatives, right, Q is F sub y, and I need to take a partial derivative of that with respect to x. And P was F sub x, and I need to take a partial derivative of that with respect to y. This component test right here is essentially equivalent to Clairaut's theorem from 14.3 that says that mixed partials need to be equal. So that's what this is doing here, is if you have your mixed partials being equal, then it means that they come from some function, that there is some f out there that we can solve for and try to find the potential function. So that's what this is doing here. So, but we'll be doing this test here a fair amount, right? Part A here, show that f is conservative over its natural domain. We will use the component test. So any questions about this before we have an example? All right, example time it is then. So starting off with, show that f is conservative over its natural domain. So again, the first component is going to be P, the second component is going to be Q. I would like to show that this is a conservative vector field. And so I'm going to calculate out P sub y first. And let's see, derivative of cosine of y is going to be negative sine. And we have this e to the x, again, that's constant with respect to y. That's just along for the ride. And then plus y. So when I take the derivative of that with respect to y, I'm going to get plus 1. Okay, so there's my P sub y. How about my Q sub x? So if I'm now looking over at Q and taking a derivative with respect to x, let's say I'm going to get 1. The derivative of e is itself. Again, this sine of y is just constant. It's along for the ride. And the derivative of 3 is going to be 0. And so if we look at this, I guess they're in the opposite order here, but they are the same, right? So P sub y is equal to Q sub x. So this is conservative by the component test. So I've now shown that F is conservative. Now is the new bit here. We need to think kind of systematically about how can we, in general, find potential functions. And so we're going to do it for this specific case first, and then we're going to try to bottle what we came up with and try to come up with a technique in general for finding potential functions. So again, if this thing is a potential, if there is a potential function, then this vector field must be a partial derivative with respect to x, comma, a partial derivative with respect to y. My goal here is to find what f is. So my thought process is I'm going to take the first component here, which should be f sub x, and then I'm going to try to undo my derivative with respect to x, aka I'm going to be doing an integral, right? I'm an antiderivative. So let's go ahead and start this up. Here we go. So I'm going to integrate, and this was e to the x cosine of y plus y, and I'm going to do my integral with respect to x. After all, this first component, again, I copied down p here. This should be f sub x. This should be a, when someone took a partial derivative of the potential function with respect to x. So I'd like to undo that by doing an integral with respect to x. So when I integrate this thing, it's not too bad, but again, just like taking partial derivatives, you kind of have to, again, hold the other variable as constant. So I think we get something like this. The integral of e to the x is still e to the x. That cosine of y is along for the ride. And the integral of y, again, this is constant. You have to think of it like 5. So if I integrated 5, it'd normally be 5x, right? So in this case, y, it's going to be yx, or I wrote it as xy. Now, there's one last bit here, is that normally when we integrate, we have plus c, right? Plus a constant of integration. The annoying thing about when you do partial derivatives, and in this case, kind of like a partial integral sort of deal, is that we integrated with respect to x. So when I talk about plus a c here, these are constants with respect to x. So that means that this is not necessarily a true constant. It could have any number of y's in it, and this x integral would not be able to detect it. And so what I'd like to do is, and what the textbook does anyway, is call this g of y. So we have a constant with respect to x, but it's a function, right? Because it can have any number of y's in it, and the x integral or the x derivative can't detect it. So for instance, just quick example, this is wrong, but I mean, if this was y squared plus 5 or something like this, right? It could have any number of y's in it. And again, if you took a derivative with respect to x, you would get back to where you started. You have no way of detecting these with just an x integral. So that's why we need this extra bit, and that is some number of y's. Okay, so now the next bit is, well, what is that function, right? Because I've only used half of my information. So I need to also use this bit up here that we know what the derivative ought to be if we took the derivative with respect to y. So I have a guess of what my, again, we integrated this thing. Oops. We integrated our x partial derivative with respect to x, and this should give me a guess of what the potential function is. The only problem is that I have still an unknown, so I need to figure out what that unknown is. However, we know that if we take a y partial derivative of this, this should be equal to q, the second component of our vector field. So let's go ahead and take a y partial derivative, and I'm going to have, let's see, e to the x is along for the ride. The derivative of cosine is negative sine. The derivative of xy, again, with respect to y here, is going to be x. And then this is going to be g prime of y. Again, there's only one variable here with y, so I can use the prime notation if I want. And this here ought to be equal, if life is going well, to q. So let's go back up here, and q was x minus e to the x sine of y plus 3. So now we can see that quite a lot of this is lining up. This is going well. That we have an x here, we have an x here. Good. We have a negative e to the x sine y. We have a negative e to the x sine y. The only piece that doesn't have a friend, I suppose, is the 3, right? And so this is what g prime of y is going to be equal to. And so if I'm interested in what g of y had to have been in order to substitute in there, well, then I can just undo this derivative. Again, this was a y derivative, and there's just y's here. So if I undo this derivative by integrating here, I'm going to have 3y plus a true constant should be equal to g of y. So we're just going to undo our derivative here to get what g of y needs to be. So if I plug this in up here, I can get f is equal to e to the x cosine y plus xy plus 3y plus a true constant. However, in the wording of this problem and whatnot, and how we're going to be using the fundamental theorem of line integrals, right? It doesn't say find the class of all potential functions or find the antiderivative in general. It just says find a potential function. So I'm going to go ahead and choose my k here to be plus 0, right? Or I'm just going to drop the k. But if it said, find, all potential functions, then you would want to have that plus k there. But in general, what we're going to do is, just use the potential function to evaluate out a line integral. So we just need one of them. So I'm going to choose plus 0. All right, so that's my final answer for B. And then the last bit here, I'd like to evaluate out a line integral. So let's do that one together, and then I'll ask if there are any questions. So we did all this work because we have this fundamental theorem of line integrals. This is leading us to the fundamental theorem of line integrals, which again says that if you want to evaluate out a line integral for a conservative vector field, that you can find a potential function and then just do f of b minus f of a. We found exactly what our potential function is. We just need to know what our starting and ending point are, right? What is our a and what is our b? So if I go back up here, we have some parametrized curve, and we have a starting and ending time, but we need a starting and ending point, right? So I need to know what a is and what b is as a starting and ending point, right? I need to plug in x's and y's here. So in order to get the starting point, I'm of course going to plug in the starting time. So if I plug in 0 into this, I'm going to have 0 and sine of 0 is 0. And if I plug in my ending time, I'm going to have 1 sine of 1. So now I've been able to convert my starting and ending time to starting and ending points, right? With x and y coordinates and all that sort of stuff. And these are going to go in nicely into this thing that wants to eat x's and y's, right? So this is going to be what? F of 1 sine 1 minus f of 0, 0. And again, we have our potential function. So let's go ahead and do our best to plug these things in. So let's see, I'm going to have e to the first power cosine of sine of 1. It's a little bit annoying. X times 1. So that's going to be x times y. So 1 times sine of 1 plus 3y's, 3 sine of 1. All right, plus 0, minus f of 0, 0. So when I plug in 0 for x and for y, well, this first bit actually is 1, right? E to the 0 cosine 0. That's all 1. But after that, we got a bunch of zeros. So my final answer here, not the most beautiful thing ever, 4 sine 1 minus 1. And just as a reminder, we are in a calculus class. We like it when the derivative of sine is cosine. This is only true if you were in radians. So that 1 there, the sine of 1 is sine of 1 radians, right? It's not degrees. So make sure your calculator is set in degrees mode. An easy way to kind of get frustrated in web work and all that sort of stuff is if you have your calculator accidentally in degrees when it should be in radians. And of course, even worse for the quizzes and the exams, right? Where the worth more points and all that sort of stuff. Last thing I want to bring up just to kind of showcase an interesting point, and then I'll open the floor to questions. So if someone else chose a different potential function, right? I chose plus 0 here. Well, let's suppose that someone else decides, I want to do plus 5, right? Then when you do your f of b, it's going to have a plus 5 here. And when you do your f of a, it's going to have a plus 5 here. And so what you're going to end up with is that plus 5, subtract away that plus 5, we're all going to get the same answer. So no matter which potential function you choose, whether it's one with plus 5 or plus 0 or whatnot, we all get the exact same answer because of the subtraction, because it's f of b minus f of a. So no matter what potential function you choose, you're going to get the same result. And that's kind of why it's okay to just choose 0 there, right? I chose k equals 0 for my constant, but if you want to choose another one, go ahead. All right. So erased one too far here. Questions about this example here? Well, there'll be chances for more questions coming up, but let's try to bottle what we've done here into a box. So technique for finding potential functions. So the first thing that we did is we took our first component for our vector field. Again, this should have been f sub x, since it's a conservative vector field, and we integrated it. This gave us a candidate for a potential function, but we still had an unknown, right? So after we did this integration, we had something close to f, but we still had this unknown bit. We didn't know how many y's were there exactly because we integrated with respect to x. It wasn't very good at detecting y's or other variables. So the remainder of the time we spent trying to solve for, well, what is this unknown piece? In order to do that, we took the derivative of our result with respect to y, and we set that equal to our second component for our vector field, q. After all, this should be equal to f sub y. Then we were able to solve that for g prime of y. Turns out that was equal to 3 in our case. And once we had that, we integrated with respect to y in order to undo that derivative and figure out what it must have been to start. So that gave us our final result of 3y plus a constant of integration. So that gave us our g of y. So this right here is a good technique that we can use in order to find potential functions. All right. Any questions on this here? Oh, stretch. Fair enough. Well, I'd like us to do another problem. This one I'd like to give you an opportunity to take, so maybe like 2 or 3 minutes. I understand it's taken a little while to do these problems, but 2 or 3 minutes. First, show that it's conservative using the component test. Then find me a potential function. And then probably all together we'll do the evaluation. But I want to give you at least time to, first of all, verify that this is conservative, and then start to try to apply the technique that we just wrote down to come up with a potential function. So 2 minutes or so, get as far as you can. Another 30 seconds or so. Again, just get as far as you can. All right, so while you all were working, I at least did part A. This is, not too terrible of a problem, right? All polynomials in this case. So the p sub y, again, p is our first component, taking a partial derivative with respect to y, we got 2x. Q is our second component, so taking a partial derivative of that with respect to x, we get 2x as well. And since p sub y is equal to q sub x, by the component test, we know that we have a conservative vector field. So that is part A done. Part B, a little bit longer, we need to find the potential function, right? So we're going to go ahead and start off by coming up with a candidate for our potential function by integrating our first component. So 3 plus 2xy, and we are integrating this with respect to x. After all, this is supposed to be f sub x, since this is a conservative vector field. So when I integrate this thing, I get 3x plus x squared y plus a constant of integration. And this constant of integration is just anything that's constant with respect to x. After all, I did an x integral here. So this is our g of y bit. So this is a candidate for our potential function, but still it has some unknowns. And so I need to take the derivative of this and get f sub y. Doing that, I'm going to have what, x squared plus g prime of y. And if all is going well, this ought to be equal to q, right? So I'm going to go ahead and look at my second component here, x squared minus 3y squared. X squared minus 3y squared. After all, q, if this is a potential function for a conservative vector field, then q needs to be f sub y. Just like before, we see that there's some stuff that's lining up quite nicely. We can cancel that out. The stuff that's remaining should all have y's in it. And so when I integrate this with respect to y, this is going to give me that my function here is going to be what, negative y cubed, plus a true constant of integration. I can take this and plug it back in, and we're going to get f is equal to 3x plus x squared y minus y cubed. And if it was asking for all of the potential functions, I would include in that plus k. However, it's just saying find a function that satisfies that, it's a potential function. So I'm going to choose my k as plus 0. So this right here would be my final answer. And of course, right, just like when we were doing antiderivatives back in Calculus 1, if you have the time, right, if, on a quiz and exam, if you're looking for ways to check your work, you can take the derivative of this with respect to x, and you should get p. And you can take the partial derivative of your answer with respect to y, and you should get q. After all, that's what it means to be a potential function, right? That the gradient of this potential function should be your vector field. So it's a nice way to check your work, again, if you have an extra 2 minutes or so. The last bit here is we need to evaluate out a line integral. So again, this is kind of building up towards something. The fundamental theorem of line integrals says that if you have a nice conservative vector field, which in this problem we do, then we're going to have f of b minus f of a. So again, I need to know my starting and ending point. So if I switch over here, I have a starting and ending time, but the question is, what is my starting and ending point? Well, I can plug in my starting time of 0 into my parameterization. And let's see, e to the 0 would be 1, sine of 0 would be 0. And e to the 0 is 1, cosine of 0 is 1. So 1 times 1 is 1. So there's my starting point. My ending point comes from, well, my ending time, pi. If I was to plug this in, well, let's see, e to the pi is nasty, but okay. Sine of pi is 0. Okay. Next up, e to the pi, still complicated thing here. And cosine of pi is going to be -1. So that right there is my ending point. So this is what I'm going to be plugging into my function, f of b minus f of a. So plugging this in here, we're going to have what? 3x plus x squared y, e to the pi with a negative sign, minus y cubed, negative e to the pi cubed. So that is my f of b. And now I need to subtract away f of a. So a is 0, 1. So everywhere I see an x, I'm going to plug in a 0. Everywhere I see a y, I'm going to plug in a 1. So again, I'm going to have 0 plus 0 minus 1 cubed. So first off here, it looks like I have what? 3 negatives, 4 negatives. So this is going to be positive. And when you have powers raised to more powers, they multiply. So when I have it raised to the pi and then raised to the third, right? So this is going to be just e to the 3 pi. Then we're going to subtract away a -1. So this right here will be my final answer. Yes, question. A, I got from plugging in my starting time into my parameterization. So I took my starting time of 0 and I plugged it in. And again, just everywhere I see a t, I'm plugging in 0. So my first component becomes 0 and my second component becomes 1. So this method here that we've given for the technique for finding potential functions is relatively straightforward to write down. Again, we can bottle it quite nicely. And so we've been able to put it in this box here. However, especially as we move on and do this for 3 variable functions with x's, y's, and z's, the problem is if there are z's involved, then after you integrate with respect to x, again, this is a constant function with respect to x. So that means that not only does it have y's in it, but it also has z's because z is constant with respect to x as well. So that makes this complicated, right? And so I've included, I mean, we won't go over it in great detail here, but as the final page, an example from our book here that does this method, right? And it has x's, y's, and z's. And you can see that after you integrate with respect to x, you have xy squared plus g of yz. And then you need to figure this out, how many y's are in it and how many z's are in it. And you're going to use your second and third component. But again, this is quite complicated. And so what I'd like to do next is to give you a faster way to find potential functions. This one's, it's kind of harder to write down, exactly what you're doing. But I hope I can illustrate it well and you can ask questions about anything if you're confused. So with this technique, what I'm going to do is that I'm going to integrate all of the pieces kind of with their corresponding variables. So let me kind of showcase this. So last time I integrated p with respect to x. So this was integration of what? 3 plus 2xy with respect to x. And this gave us a candidate for our potential function. But what I'd also like to do now instead is I'd like to integrate q with respect to y. So this is going to be x squared minus 3y squared dy. And this should also give us a candidate for our potential function. And then we're going to kind of see what they have in common and what they don't have in common. And this will help us create our true potential function, again, a bit quicker. So if I do this, well, we've already done the top calculation. What, we got 3x plus x squared y plus a constant of integration, but it could have any number of y's in it because it's constant with respect to x. After all, we did an x integral. I'm going to play the same sort of game, but now integrating the second one here with respect to y. So when I integrate this with respect to y, let's see, x squared is going to be x squared y. And then negative 3y squared is going to become my negative y cubed. And then plus a constant of integration, but this is now just constant with respect to y. So it could have any number of x's in it. or constants, right? But it could have x's. Now, the thing here is that these are probably different functions. And so it's inappropriate to use g in this name a second time. So you can either use subscripts, right? You could use g sub 1 and g sub 2, or I'll use h. So we have h, and it could have any number of x's in it. Again, all the stuff that's constant with respect to y. So now if we kind of look at these together, I see that we have some stuff that both of these integrals were able to detect. They're both able to detect pieces that have x's and y's in them. After all, the x integral is good at finding x's, and the y integral is good at finding y's. The next bit is that this x integral did a good job of finding 3x. The y integral is not going to do a good job of knowing what that is. And so it just says there's some number of x's there, right? But that h of x there is going to be equal to 3x. This was the unknown. But again, the y's didn't know about it, but the x's did. And likewise, the x integral doesn't know about negative y cubed, but the y integral knows about this. And so if you take all these pieces and put them together, right? Both of the integrals knew about x squared y. The x integral knew about 3x. And again, this was just h of x in the second one. And the second integral knew about this negative y cubed. This right here gives us a potential function. You could do plus 0, you could do plus 5, right? Plus any true constants sort of deal. And this is the same one, by the way, that we have up here. So it gives us a similar good result. Now this probably saved us, a line of 2 or work here. And it's kind of harder to bottle and say exactly what we're doing. But of course, if we take the partial derivatives, you do get our original vector field. And so that's nice. And while this only saves us a line or 2 of work here, when you have 3 variable functions with x's, y's, and z's, this is going to save you about 4 or 5 lines of work. It becomes much more significant the more variables you have. And so the only reason that I bring up a second way to do this that's a little bit faster now is because when you do 3 variables, x's, y's, and z's, this is quite nice. But again, right, for instance, this x squared y, although it appeared in both integrals, you don't have like 2x squared y here. Again, it only appeared, you put it once, right? It's just that both were able to detect it. All right, the last thing that I want to do in today's class is showcase kind of, I don't know, an interesting, this would be a fun multiple choice, or you could do a true-false style question, like on a quiz or an exam or something like this. And so I have a curve C for a contour map of a function f, but I haven't told you what the function's equation is or anything like this. But at the end of the day, right, I'm interested in evaluating a line integral. And the question is, well, what is the value of this line integral? Notice that nowhere in this problem does it say use the fundamental theorem of line integrals. Of course, when we're here in today's class, it's all about fundamental theorem of line integrals. You're like, oh yeah, well, use the fundamental theorem of line integrals, right? But when you're on a quiz or when you're on an exam, when you have like many topics, the first thing that you need to recognize is that this thing satisfies the hypotheses for the fundamental theorem of line integrals. All right, that you have a nice function and you're interested in calculating out the integral of some derivative, the integral of the gradient. And so we're going to apply the fundamental theorem of line integrals. This is the first good idea that you need to have. So you need f of b minus f of a. And then the second thing that you need to remember is something that we covered in 14.1, which is how do you read contour maps? And so let's go back over here. I can see my curve. It'd be nice if they included the dots here, but okay, I can clearly see, right, what is my starting point and what is my ending point. When the curve starts and ends, there's an arrow to indicate the direction in which you're heading, right? So we're going to start at A and travel along towards the arrow, towards our ending point B. And remember, a contour map gives you all of the places that the function achieves a certain value. So for instance, everywhere along this curve here that's closest to the origin, right, these are all the places where the function's value is 10. At any of those xy pairs that you plug in, right, whether it's here or here or here or here, right, or of course our A, all of those places, the function's value is 10. Likewise, up at B, notice that this is on the level curve of height 50, right? So all of those places, the function's value is outputting 50. So we're going to have f of b. This is a place where the function is outputting 50, minus f of a. This is a place where the function is outputting 10. And so once we have these good ideas and know how to read our contour map and all that sort of stuff, the answer comes quite quickly. But again, this is kind of more conceptual question. I didn't have to find a potential function. I didn't have to do any integration or calculation. The question is really, what do I apply here? I needed to apply the fundamental theorem of line integrals, and I needed to read the contour map. So this is a bit more of a conceptual question that I wanted to leave you guys with. All right, that's it for today. And that's it for the new stuff for our upcoming midterm on Thursday. Again, Wednesday is going to be review day. So take a look at the review packet that I posted on D2L and come with questions. All right, I'll stick around if you have any one-on-one questions. Otherwise, see you Wednesday.